Hello everyone. Today I'll be talking to you about the reaction we'll be doing in lab this week, which is the nitration of methyl benzoate. You can see the reaction scheme here, reacting methyl benzoate with nitric acid and sulfuric acid to get our product. Before we begin, some brief safety considerations. Nitric acid and sulfuric acid are both strong acids and should be handled carefully. Both acids are also corrosive and will burn you if left on your skin. Make sure to wash any affected areas with copious amounts of water if any gets on your skin. Also, nitric acid is a strong oxidizing agent and will react strongly with organic compounds, so make sure to wash any glassware that contains nitric acid with water before trying to clean with another solvent like acetone. If any acid is spilled throughout the course of the lab, make sure to neutralize that spill with sodium bicarbonate before attempting to clean it with something else. The type of reaction we'll be doing in this lab is called electrophilic aromatic substitution. Electrophilic aromatic substitution is a reaction that involves the substitution of a substituent, which is typically hydrogen, on an aromatic ring by an electrophile. Due to the fact that we break the aromaticity of the ring, strong electrophiles are necessary for this substitution. In electrophilic aromatic substitution, substituents that are already on the ring will have an effect on where the electrophile will be located after the reaction. Groups on the ring can either be ortho-para directing or meta-directing. The image on the right shows the positioning of ortho, meta, and para relative to the R group that's already located on the ring. On this slide, we have examples of both ortho-para directors and meta-directors. So how these directing groups work has to do with resonance forms. Ortho-para groups are electron donating groups, which donate electrons into the pi system of the aromatic ring, while meta-directors are electron withdrawing groups that remove electrons from the pi system of the aromatic ring. The bottom image shows an example of this using a meta-director. When the nitronium ion is added in the para position, we get a positive charge on an adjacent carbon, which if we go through the resonance forms by moving electrons to the second resonance form, which is the one that's red, we see that both positive charges are adjacent to one another. That's an unfavored interaction and will make that immediate much more electron deficient. By contrast, with the nitronium ion in the meta position, those charges are further away from one another, minimizing the electron deficiency in the intermediate, leading to the meta product being the favored product. In this reaction, the first thing we do is a generation of our electrophile, the nitronium ion. Concentrated sulfuric acid is added to concentrated nitric acid, generating the nitronium ion through dehydration of the nitric acid. Between sulfuric acid and nitric acid, which is a stronger acid and how does that cause this reaction to proceed? For the procedure, you'll start by adding concentrated sulfuric acid to an Erlenmeyer flask and cooling that in an ice bath to 0 degrees Celsius, and then you'll add methyl benzoate. After this, using an ice salt bath to cool it again to 0 Celsius, you will very slowly add a 50-50 mix of concentrated nitric acid and sulfuric acid. You will want to keep this mixture stirring continuously during the addition, and you'll also want to make sure that you keep the temperature below 15 degrees C by adding it very slowly, or else you will get the formation of unwanted byproducts. And then after all the acid has been added, allow the solution to slowly warm to room temperature. After the solution has warmed to room temperature, pour the mixture over crushed ice. After the ice is melted, filter the product using a Buchner funnel and wash with cold water. Finally, recrystallize the product from ethanol and determine the percent yield.